Okay, so in this video I want to try and clear up some of the confusion some of us have around the concepts of resistance, reactance, and impedance, and how each of these three concepts differ from each other. So let's look first at what is resistance. Suppose I have a resistor here in a circuit, a resistor R. If there is a current flowing through the resistor and there is a voltage drop across the resistor, V, then we know from Ohm's law that V is equal to I times R. So V is the current times the resistance, and this is a simple linear relationship. This is V, this is I, and if you look at this slope here, we have delta V, and here we have delta I. So the slope is delta V divided by delta I, which is a voltage divided by a current, and this is equal to the resistance. So the slope of this is equal to the resistance, and notice that I have graphed the voltage here and the current here. You can also graph with the axis inverted, so this would be the voltage and this would be the current, and this is the more usual way of doing this. And then you look here at the slope. The slope here is equal to a current divided by a voltage, and so the slope in this case is the conductivity, is the conductance rather than the resistance. So the slope here is 1 over the resistance, which is equal to the conductance. So in this case, in case of the resistor, even if you put an AC current, an alternating current through the resistor, the current and the voltage, they are going to be in phase with each other. If this is the voltage, this is the current, and you have a voltage, you have a current, and if you have, let me do this like this. If you have, let me just change it like this. So this is, I'll do something else. So this is time, and this is the voltage, and you have the voltage doing this around the resistor. The current is going to have the same form here, a different amplitude, but they are going to be in phase with each other. So there's no phase change between the voltage and the currents for a resistor. Okay, and resistance is basically particles colliding inside the conductor. So if you have a conductor like this, you have a few atoms, positive charge, lots of them inside the conductor, and you have electrons flowing around. And these electrons will start to bump around the atoms and bump around each other as well. And this kinetic energy that the electrons transfer into the atoms will make everything shake, and this is temperature, and this temperature will generate some heat that is dissipated on the conductor. So this is basically resistive. So this creates heat, it creates heat and dissipates power. So this is basically what a resistor is. Now let's look at reactance and impedance. Now reactance and impedance are related to each other, and for AC circuits, if we have an AC circuit here, a resistance, for example, an inductor and a capacitor, this is R, this is L, and this is C. The difference here is we have one resistor, we have one inductor and one capacitor. The inductor and the capacitor are going to have reactances rather than resistances. And we write XL, which means the reactance of an inductor, and this will be equal to omega times L, where omega is equal to 2 pi times the frequency of the voltage. Similarly, for the capacitor, the reactance XC is going to be given by minus 1 over omega c. Again, c is the capacitance and omega is the frequency. Here L is equal to the inductance, by the way. And also, just for completion, we know that the capacitance of a capacitor is given by epsilon, which is the permittivity of the dielectric, times A, which is the area of the plates, divided by L, which is the distance between the plates. And this is also equal to the charge on the capacitor divided by the voltage between the plates. Okay, so this is what reactance is. Now reactance is different to resistance in that reactance doesn't dissipate power. Reactance is really like an inertia, trying to oppose the change of current and voltage in the circuit. If you try to apply a current on the inductor, it will take some time for the current to really get going. The inductor will resist the current. It will try to oppose the current by creating a voltage which is opposite to the voltage you apply around it. And so it has reactance because of this, because it resists the change of voltage or the change of current in the case of the inductor. The capacitor is similar in that it resists the change of voltage. If you apply a current on the capacitor, it will start to accumulate charge, and as it accumulates charge, it will get more and more difficult for charge to come to the plate. And it also depends on the frequency. So the first thing to notice about reactance is that they depend on frequency. So the reactance of an inductor is omega times L. So as you can see, it depends on the frequency. The higher the frequency, the higher the reactance. So the more the inductor will oppose the change of current. And the smaller the frequency, the smaller the reactance. For the capacitor, it's the opposite. The higher the frequency, the smaller is the reactance. And the smaller the frequency, the higher is the reactance. So again, reactance is kind of inertia. For example, if you have a big rock and this rock is moving in space in this direction here with a vector v, so it's moving in free space, um, it will tend to continue moving with this velocity, with this constant velocity. It will not stop unless there's a force to stop it. So it has inertia. Similarly, if it has no velocity relative to you, it will resist you trying to push it and create an acceleration. And so reactance works in the same way. It tries to oppose the current rather than just dissipating power and being the result of atoms and molecules and electrons colliding. Okay, so now we go to impedance. Now impedance, we write the impedance as Z, and we can write ZL and ZC for the impedances of the capacitor and the inductor and the resistors. Now the first thing to know is that an impedance, Z, is a complex number. So it's a complex number in the complex plane C. So Z is going to be equal to, it's a pair of numbers, a pair of real numbers, and it consists of a resistance and a reactance. So impedance is a combination of resistance and reactance. So reactance X is the imaginary part of impedance, and R is the real part of Z. So every element, resistors, capacitors, and inductors, can be dealt with in terms of impedances. A resistor also has an impedance, but its impedance has zero imaginary parts. So the impedance of a resistor is simply R, and we can also write the imaginary part as just simply being zero. So a resistor has no reactance. Similarly, an inductor has a resistance plus j omega L, and the resistance is 0. So the impedance of the inductor is a complex number whose real part is 0 and which is also dependent on the frequency. Similarly, for the capacitor, it has a resistance plus, uh, hold on, let me write, minus j over omega c, and it also has resistance 0, and its reactance and impedance depends on the frequency. Now these are for ideal elements. Ideal elements, because of course in the real world capacitors and inductors are made of real things, so they also have non-ideal resistances, inductance, and capacitances. So if you take a normal resistor like this, it will have a non-ideal resistor, will have an impedance, and also it will have a reactance. And because if a current flows in a wire, there will be a magnetic field around the wire, which is given by the right hand rule. So um, not sure which direction this magnetic field will go here. If you have a magnetic field and a current in this direction, then it will be given by the right hand rule. And so if the current is flowing along in the upward direction, then the magnetic field is going to be in this direction here, like this. Is given by the, let me draw this better here, let me draw this hand here in a better way so you can see the direction of the magnetic field. So if you have your thumb pointing out upwards like this, your fingers like this, they curl up like this in this direction, and the current is in this direction I, so the magnetic field is going to go in this direction here, which if you turn this way is counterclockwise. So if the current in the other hand is going in this direction, then the magnetic field is going to go around the other direction like this. So anyways, this is a divergence. So this is just to show that even a normal wire has an inductance because it creates a magnetic field around it, which stores energy in the form of a magnetic field. So, and also capacitors have inductance, and so on. So non-ideal elements, they do have impedances, and a capacitor also has resistance, for example. But if we in electronics we usually talk about ideal elements, because in a circuit, if you have a capacitor here in a circuit, for example, and you want to model this capacitor, then you start to add the resistances of it. You can add the non-ideal elements as other ideal elements in the circuit, and in this way you can model your circuit better. So as as we have seen, an impedance is composed of a resistance R and a reactance X. So now, when we are dealing with AC circuits like this, and you have, for example, a resistor, an inductor, and a capacitor, RLC, you apply, if you apply a voltage here, so usually we say that the voltage is VI e to the j omega t is a complex voltage. And this complex voltage has a magnitude, it has an amplitude, and it has a frequency, and it has a phase. So it starts like this. It has a certain phase, which is how um, whether the voltage is shifted to the right or to the left. It has an amplitude A and it has a frequency F. If you apply a certain voltage then around the circuit, the voltage around the capacitor and the inductor, they are going to be shifted in regards to the current flowing through these elements. So this is the basic difference between the impedance and the normal just resistive uh, elements. If you have the, you can also deal with the impedance plane. So you have Z here, you have the imaginary part here and the real part here. This is minus J, the minus J direction, this is the J direction, and this is the resistive direction. So along the real axis we have resistances. Along this positive axis we have inductances, and along the negative axis here we have capacitances. And this is because if you remember, the impedance is equal to R plus omega X, and for the capacitor X is equal to minus 1 over omega C, so XC, and XL for the inductor is simply omega L, and therefore the inductance of an element which has zero resistance and only has a capacitive reactance, this is going to be equal to minus J over omega C, and minus J over omega C is going to be some point along this axis here. Similarly for inductors, it's going to be a point along this positive axis, and for general impedances it's going to be a vector here, R plus JX. Can be a vector anywhere, and depending on, it cannot be negative, sorry, because resistances are not negative, so we only deal with the positive part here. So if the impedance is on this quadrant here, if we have an impedance here, then this is going to be inductive, mainly inductive. It will have a resistance, but the imaginary part is going to be an inductance. Similarly, on this plane here, we have capacitive impedance. Okay, so every impedance can be represented in the complex plane like this. And now going back to the point here about shifted voltages and currents, since the impedance of a capacitor is going to be, of an ideal capacitor, is going to be minus J over omega C, and if you remember Ohm's law, we also have a form of Ohm's law for a alternating current in voltage circuit. So we know that V as a complex voltage is going to be equal to I, the complex current, times Z, which is the impedance. This law also works for alternating current circuits. So if we deal with the capacitor which has this impedance, then we know that the voltage is going to be equal to the current times minus J over omega C. Now look at this formula. This says that the voltage is equal to the current times minus J over omega C. Now when you multiply a complex number in the complex plane, first if you multiply it by J, if you take this complex number Z and you multiply it by J, then this is equivalent to rotating it by 90 degrees in the counterclockwise direction. So this is pi over 2 degrees, and this is Jz. Now similarly, if you multiply this number by minus J, then you're going to be rotating it clockwise along the clockwise direction by minus pi over 2. So this is minus Jz. So if you look at this formula, it's saying that for a capacitor, if you have a current going through it with a frequency in a certain phase, the voltage through it is going to be the current rotated by minus pi over 2 degrees. So this means if you have, let's graph here the time and current for, no, hold on. We have time, and here this axis here will be taken to be either the, I'll graph both the voltage and the current uh, through this. And so if you have a current here, which is a, for example, a cosine wave like this, so this is I, the current I. According to this formula, the voltage is going to be the current I shifted by minus pi over 2 degrees. What does this mean? This means that if you take this current, you shift it by minus pi over 2 degrees. That means if you have, for example, a cosine of, for example, omega t minus pi over 2, is this shift, this wave is going to be shifted to the right by pi over 2 degrees. So if you take this guy, this is equivalent to shifting this by pi over 2, or by minus pi over 2 degrees, like this. So this is the voltage. This is the voltage. So the first thing to notice is when we're dealing with alternating current circuits, Ohm's law will imply that there's always a shift between voltage and current for purely reactive elements. So basically this is the difference between resistance, reactance, and impedance. Again, a reactance is the imaginary part of the impedance. And the most important thing to know is that for purely reactive elements, the current and the voltage are always going to be out of phase between each other. So I hope this has clarified some of it. I don't want to keep this video very long, so thank you very much for watching.